Hello, everyone. It's Mr. Vallejo. Welcome to class. Today, we'll be tackling the topic of climate change. Let's go ahead and get to our PowerPoint for today. Share the screen and let's take a look at climate change. In today's talk about climate change, it seems like more than the first half of the lecture will be everything I ever studied in my Earth and Space Science class at the UCLA many, many years ago. But you need to understand the characteristics of the atmosphere in order to properly understand climate and climate change. So let's go ahead and take a look at that. This is based on chapter 15 in Cunningham and Cunningham's environmental science textbook. And so the topics that we'll be covering today include these listed on the screen. We'll be taking a look at the atmosphere and how weather is experienced in different regions of our country. We'll take a look at natural climate variability, but then unnatural climate variability comes into play when we take a look at anthropogenic climate change, which means that it's human-induced, and we'll take a look at the effects and the solutions as we go through today's talk. All righty, the atmosphere is a very complex system, but first, before we go into the characteristics of the atmosphere, let's define the terms that we need to use. Weather is a short-lived local pattern. And when you're taking a look at weather, you do incorporate the idea of temperature and precipitation. Many of you will look back and remember that when I spoke about biomes and ecosystems, that the determining factor, the characteristics of the area that are important when determining which biome you might be in is our temperature and precipitation. So weather is temperature and precipitation due to circulation of the air in the first layer in the troposphere, whereas climate is long-term patterns, not short-term, but long-term patterns of temperature and precipitation. So weather is what you experience on a day-to-day basis, but climate is what your expectations might be on a yearly basis or even in a multi-year schedule. So now that you know the difference between weather and climate, what we're going to do is we're going to take a look at the atmosphere. And you may know that the atmosphere is made up of mostly nitrogen, then oxygen. And then there are other molecules that are floating around in the atmosphere that is significant when we talk about climate change. Okay, so it's going back to that slide. I have a little poem that I use to remember the parts of the atmosphere, and it goes like this. Nitrogen is 78, oxygen is 21, all the rest is less than 1. So nitrogen gas, 78% of the atmosphere. Oxygen gas is a little short of 21%. And then water vapor, depending on where you are on the earth, it might be 0 over a desert, might be 5% over an ocean, about 5%. Aerosols that are scattered throughout the atmosphere, also important when it comes to determining climate change. Argon, usually the given number is about 1%. So if you look at it, if 78% nitrogen, 21% oxygen, water vapor 5%, look, we're already over, right? And then you have solid particles, although they might be very, very small particles. Here in Southern California, where I live, we used to kid about the city of Santa Barbara because where I live, you would look out towards Santa Barbara and you get these beautiful red and purple sunsets. That's because of, in the last 10 years, there's been many, many fires in that area. As you know, California, one, uh, one result of climate change is the amount of wildfires that we have here in California. So, so particles are important because they would cause those red and purple and beautiful orange colors in the atmosphere. But you know that that's not such a good thing, especially for all the living things in that part of California. So you can also see that less than 1% of the atmosphere then is going to be greenhouse gases, which are responsible for climate change. And we'll see that usually we talk about carbon dioxide, but there's also methane in there. And those are significant when we take a look at climate change. All right, as we look at the atmosphere, there are 4 different layers of the atmosphere. Actually, NASA says there are 5 different layers. And if NASA says something, you gotta listen. But going from the bottom up, from the ground up, you have the troposphere. The troposphere is immediately adjacent to the Earth's surface at the 0 to about 10 miles up. Says here ranges in depth from 18 kilometers over the equator to 8 kilometers over the poles, then out over the pole. If you don't speak metric, then I remember that when I used to run a 10K, that was 6.2 miles. So 20K is going to be about 12 miles. So as you can see, it's 12 miles at the high, and then it gets thinner over the poles. So I like to remember it this way: 0 to 10 for the first layer, 10 to 50 for the second layer, and so we'll see the second layer in a second. So that's the troposphere. Convection currents redistribute heat and moisture around the globe. We'll see that in several slides that are coming up. And the air temperature drops rapidly with increasing distance from the Earth. This creates a problem in my local area. We have sometimes what are called temperature inversions. And the simple explanation is that the air close to the ground is warm as the sunlight is absorbed by the ground and the air goes upward, then the temperature, as you increase in altitude, the temperature increases. Oops, check that. The temperature decreases. Think of it on let's say, do you remember when you were a kid and you swam all day, those of you in warmer regions, and you got out of the pool and wanted to warm up? Well, what we would do when I was a kid is we would go to the municipal pool, which was actually called the municipal pool. Yeah, but we didn't know that. And so we called it the municipal. And when we got out of the pool after swimming for 2-3 hours, we wanted to warm up, we would get out and put our towels on the concrete and then lay on the concrete all spread out. And that would warm us up. Why? Because the Earth has that heat from the sunlight, from the infrared solar energy, and so that energy is coming back to us as heat. So down by the ground, it's warm. As you go up, though, in the troposphere, which you see as the temperature is decreasing. Okay, and then there's the tropopause where it's no longer decreasing and seems to kind of plateau right there. But that means that we are ready to go to the next layer, which is the stratosphere. And the stratosphere up to about 50 kilometers again. So if you take 6.2 miles and and multiply that times 5, that's about 30. So 0 to 10, 10 to 40, about, these are iffy numbers, approximate numbers, but to help you remember them, sometimes we take a look at miles and say 0 to 10 and 10 to 40 and or maybe 10 to 30 and then 30 to 50 for the next layer and 50 to 300 for the last layer. Stratosphere, has almost no water vapor, but 1,000 times more ozone than the troposphere. Now, this is the bottom part of the stratosphere is where the ozone layer is. Ozone is a pollutant down low. I know that because I live in the Los Angeles metropolitan area. And one thing they track, and one reason they say we have the worst air in the whole United States is because our ozone layers are high. Now, isn't ozone good? Well, not when you're breathing it, but ozone is good when it's in the stratosphere. When it's in the second layer of the stratosphere, second layer of the atmosphere, at the bottom of the stratosphere, then that's where the ozone layer works for us and absorbs the ultraviolet light, which warms the upper part of the stratosphere, blocks those UVA and UAB waves, and so the ozone layer protects us that way. Okay. Ozone is being depleted by pollutants, including freons and bromine. It was years ago when we stopped using freon for many different things, and so we have implemented different types of chemicals for other uses. There used to be a big use in the United States of a chemical called CFC, and that's a group of chemicals that the CFC stood for chlorofluorocarbons, and those CFCs would be released from a spray can, and they were the propellant in an aerosol can, and that going into the atmosphere would take out 100,000. One molecule of CFC, it said, could take out 100,000 ozone molecules. So starting in the 80s, we thought that there was maybe a reduction in the ozone layer. So they called that the hole in the ozone layer. And the strict definition is that it's a 50% reduction. So we see that occurring over Antarctica starting around 1980 or so. You can take a look at that and see the pictures of it. It looks like that is something that is actually happening. Is there a significant impact of the ozone hole? And it was predicted that there would be more cases of, say, skin cancer in South Africa and Australia, being there in the southern hemisphere. There has been a slight increase in cancer in those areas, but some would say, on the other hand, that the hole in the ozone layer is cyclical, and it would form naturally anyway. So now research says that it has increased, and most likely it's due to human activity. So we have the troposphere, the stratosphere, and then we have the mesosphere. The mesosphere, meso means middle, so middle layer where the atmosphere diminishes in temperature. So another way to remember this is say with the phrase down, up, down, up. And so in the first layer, the troposphere, the temperature goes down, and then in the stratosphere it goes up, and the mesosphere goes down. That's what it says right here. The temperature diminishes again. And thermosphere, hence the name thermo, its temperature's going up. And what's happening in thermosphere, which is sometimes called the ionosphere, in the lower layer especially, then the temperature is going up because most of your gas molecules are going to be pulled down towards the Earth because of gravity. And so 80% of the atmosphere, no, 80% of the molecules in the atmosphere are going to be in the troposphere. And as you go up, you're going to get less and less of that. That's why we have weather in the troposphere, but in the stratosphere, you hardly see any of that because you're sitting on top of the clouds. And as you go to the mesosphere, you don't see any of that. You're lucky to see, if you were just sitting there in the mesosphere, you might see you look down low, you would see some weather balloons and experimental aircraft. That's a mesosphere. The thermosphere, again, is the temperature is getting higher because the very few molecules that are in the thermosphere are being bombarded by solar energy, and that is what's increasing the temperature. I was saying that NASA said there's a fifth layer. It's called the exosphere, and others would say, well, that's basically outer space. So, and then here is some information about the ionosphere with the northern lights in it. Okay, here's your classic diagram that shows you that in the troposphere is going down, and it's one going up, and then down and up, and then we have 0 to 10, 10 to 30 or 40, 30 to 40 to 50, and 50 to 300. So those are the elevations, and this is the trend of the temperatures as you increase in altitude. And then where you have the term pause, that's where you have a straight up and down line. That means that the temperature really isn't changing right there. So those are the layers or the boundaries between these different atmospheric layers. All right, so now you know something about the atmosphere. And we also have an idea of the absorbed solar energy. These are approximate numbers, but they're pretty close. About 1/4 is reflected by the clouds, by the atmosphere. Of all the energy that comes from the sun that hits the earth, another 1/4 is absorbed. So we have 1/4 reflected and 1/4 absorbed by molecules that are in the air. Carbon dioxide is a really important one. Methane also, not neglecting water vapor also. As water vapor absorbs the solar energy, then that is seen by us as the weather. And then it says about half reaches the Earth's surface, and then some of the solar energy is reflected back by portions of the Earth's surface. And let's see here. And that's because different surfaces of the Earth reflect things differently. Like, something that's really dark might absorb the heat, just like you going outside on a sunny day with a black shirt on versus a white shirt on. You might feel a little bit cooler with that white shirt on because it's reflecting the solar energy. But if you've got a black shirt on, then you might feel a little warmer because it's absorbing that energy. And it's the same idea with the Earth's surface, whether it's covered with water, the ice and snow and ice is going to reflect that. And so this diagram here from the environmental science textbook shows you some numbers. One number and here is a table showing you the albedo of surfaces. And so you can see that here the white surfaces have a greater percentage of the reflection of the light, but then things like black soil, 3%, and that makes sense, but the average is 30. So, that means if the reflection is 30, that means 70% of that 50% is going to be absorbed, and then as it comes back from the ground then it's going to be coming back as heat, which is a form of energy. So here, most solar energy reaching the Earth is near infrared, and then when it comes back, like I said, and then when it comes back up into the atmosphere, it's going to come up as heat. Energy emitted by the Earth is mainly far infrared radiation, and there it is right there. It's heat. To remind you, the electromagnetic spectrum, there's the visual portion of the electromagnetic spectrum, which is the colors of the rainbow. Roy G. Biv, if you remember. So you have red meaning, R meaning red, orange, yellow, green, blue, indigo, violet. So on the other side of violet, you have ultraviolet. So those have more energy. And then on the other side of red, you have infrared. And so infrared energy has a longer wavelength. It's not in the visible wavelength that we don't perceive infrared energy visually, but it has a longer wavelength, which means it has less energy. That's why when you point your remote control at yourself, you're not injuring yourself because there's not enough energy to cause any problems. Alrighty. So the greenhouse effect is what it's the old term, the archaic term, if you will, for global warming. With the greenhouse effect, it says here it's a natural phenomenon where the atmosphere transmits sunlight while trapping heat. If you can think of a greenhouse, if you've ever seen a greenhouse, which is it has the frame of a house, but it has a clear plastic or acrylic or glass walls and a roof. That's where you might grow some plants. Well, that's not necessarily a bad thing. That's what supports life. However, it does increase the temperature. So that is, this has been known for years, for decades, the greenhouse effect. The important greenhouse effect gases we know are carbon dioxide is the one you're going to hear about the most, but water vapor and methane also retain heat. We can we can influence the greenhouse effect, and we have as humans by burning fossil fuels, by combustion of fossil fuels, and that creates extra carbon dioxide, and the carbon dioxide concentration in the atmosphere has increased dramatically ever since the Industrial Revolution in the 1860s, 70s, up until this point in history, but more so in the last 50 years or so. Also, deforestation destroys carbon sinks, and that was especially a bad problem in the 1990s when people would go into tropical rainforests and just cut all those things down, burn them off, take the ashes, dig them into the soil, and grow some crops for 3, 4, 5 years. When the soil got bad, because tropical soil is not very nutrient rich, then you would go somewhere else and do it again. And so you can still see satellite images of plots of virgin tropical rainforest areas that experience this problem. All righty, let's take a look at convection currents and movement in the atmosphere, how that's related to pressure, and how the atmosphere at different temperatures can hold different amounts of water. Basically, when the atmosphere cools, it drops its water. And as you know, heat rises. So what happens is that as around the equator, because it's getting hot, yeah, from the sun that's hitting the earth straight on instead of at an angle. Well, that insolation, it's called, that increase in insolation makes it so that the air at the equator is warmer. And so as that air is warmer, it rises up. And as it gets pushed toward either pole, it's going to cool down. And as it cools down, it has to dump its water. This is why the tropical rainforests are found around the equator. And so this air will get pushed uh, toward the poles, and then uh, at a latitude of about 20 or so, both north and south, then it's going to start to come back down. And as it comes back down, the air is able to hold more water vapor. And so it essentially sucks out the water from the atmosphere. So when it gets to the ground, it's not raining right there. So this is why the deserts are typically at a latitude of 20 plus, both south and north of the equator. So, it's called latent heat as uh, the heat that is in that atmosphere, especially in the water vapor. But that is essentially how convection works, and you have those cells of movement uh, in the air, and so at the equator you have the air moving up, and then it goes toward the poles, gets a certain latitude, and then start to come down. And again, you see the tropical rainforest and the deserts are a result of this air movement. Oh, look, here's a diagram of it. Here's a cell. Here is the air moving up. The warm air is moving up, and then as it gets moved out, this is the tropical rainforest. Okay, but then right over here at 20 plus, you're going to see that this air comes down uh, because this is pushing, this air right here is getting pushed over towards the equator. And then as it goes towards the equator, it's getting heated up. As it gets heated up, it moves over there. And that's how you get the movement going. Well, over here, this is where you get your deserts. Look, this is in the United States, the border of Mexico, right here, because you're going to get your deserts right there at 20 plus. Okay. All right. Resulting latent heat causes air to rise, cool, and lose more water vapor as precipitation. Like I said, there's a lot of content in this talk concerning the atmosphere, and like I said, it's almost everything I learned in Earth and space science. Um, so so there's good information here. All right. It also has to do with pressure, and when you have a high pressure area, it's essentially pushing the air towards a low pressure area, and it's not just two dimensions. The pressure is lower uh, at a higher altitude and the pressure is higher close to the ground, then the air is going to get pushed up, as you saw in the previous diagram. Alrighty. So right, we call these winds when we have movement of air. Right. So in this diagram here, you can see that. Oops. You can have here's the air getting the air getting warmed up. As it gets warmed up, it needs to drop all its water, not all of its water, but it needs to drop its water. It gets pushed over here. The air moves towards a high pressure area over here, and then as the air warms up, the moisture comes out of the atmosphere. So then you don't have any rain right there. So that is the diagram right there for convection currents. Now, weather events follow general patterns, and they're predictable, less predictable in in immediate days. Uh, Physical conditions in the atmosphere over short time scales. That's what we define as a weather. But remember, compare that to the climate, and climate is long-term uh, expectations in temperature and precipitation. Speaking of precipitation, why does it rain? It says here, air cools as it rises and water condenses as air cools. So the water condenses as air cools, and chemically speaking, less water can be in the form of water vapor when the atmosphere is cooler. All right, the pressure decreases as the air rises, and so this also causes the cooling. And also, you have to have something in the atmosphere. This is the uh, this is the science behind the background of cloud seeding, and you've got to have tiny particles that the water molecules can coalesce around, and then as they do that, they'll condense and they'll come down as liquid water or rain. Here's a mention of the Coriolis effect. The Coriolis effect, as the air moves to the north or to the south, away from the equator, it doesn't move just straight north or straight south. You have to keep into account the rotation of the Earth. So it's going to be in a curved pattern, and essentially the curving pattern results in the fact that the Earth rotates in an eastward direction as the winds move about it. And that's called the Coriolis effect. They used to say that if you flush a toilet in Australia, it'll go counterclockwise. Well, it's not that. Studies that later showed that really it's the the shape of the toilet or other factors were more influential. But that's a Coriolis effect. Okay, so all right. Here's a slide on jet streams, and it's not just the air on the ground that we're interested in. Just like it's not the circulation of water at the top of the ocean. We need to look at it as a three-dimensional object. And so it says here the hurricane force winds at the top of the troposphere is what the jet streams are. And so the jet streams can totally influence the atmosphere also. And you can see here's the climate expectations for the jet stream. So you can see over here, depending on where you live, now this is for the polar jet stream. There are other jet streams, like if you live in Florida, I remember going to Florida and walking into the water and saying, and what was it? It must have been August. In August, it was like bath water. Why is that? Well, because the circulation of the ocean pattern that's helped by the jet stream that's going up here along the eastern coast of the United States. It's coming up from that warm area south of Florida and coming up on the right side. So this is a map of the polar jet streams, and the polar jet streams certainly affect the weather patterns. Ocean currents also modify weather, and that's, I guess, what I was speaking of. But it's not just on the surface, but also it would be, if you can take a look at other areas, if you look at off the coast of Chile, there is a upwelling of nutrients from the bottom of the ocean that come up as the water hits South America. It brings the nutrients up, and we call that an upwelling. Okay. And many people rely on seasonal rains. As I speak here in Southern California, in California, actually the whole state, we are in a drought. We're in the third year of the drought, which is a problem when it comes to things like the forest wildfires and such. In India, they have monsoons. It's a seasonal reversal of wind patterns caused by differential heating and cooling rates of oceans and continents. Most prevalent in subtropical and tropical areas. I think there's a map on the next slide so we can see some of that. And it has to do with it's a seasonal rainy pattern. And if you take a look, let's look at the map. There it is. As this water comes from the Indian Ocean, okay, it has a lot of water in there because it's over water. And so chemically speaking, this water has a higher percentage of water vapor, but as it comes over here, and especially as it hits the largest mountain range in the world, the Himalayas, then it's forced up. And as the air is forced up, it cools, and as it cools, it can hold less water, so you're gonna get a really rainy area right here. And because you have a very rainy area right here, you can see the rivers start to flood. And so that's why you get these floods in the monsoons in India. Okay, so that is an expectation that the climate in India, that you have that type of pattern. Okay, all right. Next slide says frontal systems create local weather. And so let's take a look at that. This is a discussion of fronts. And you have a cold front, and you also have warm fronts. The cold air is heavier, so as the cold air and warmer air meet, the cold air sinks, and the warm air goes on top of that. And so when that happens, you can get some really good rains. It says here thunderstorms. On the other hand, if you have a warm front and the warm front is moving, it's going to move over a cold area. And so when you have that, you might see a different cloud pattern, and you'll see the feathery clouds called the cirrus clouds as part of that cloud pattern. And if you take a look at it says here it can bring days of drizzle. Sure. Over here, here's the warm front, and these are the feathery clouds. I'm talking about the cirrus clouds. But where you get the nimbocumulus clouds and the altostratus clouds, that's like right here and right here. That's where you're going to get the rain. Okay, the altostratus are really high in that picture, not so high in this one here. But especially with the nimbocumulus clouds, those are the ones that have a lot of association with rain, and so you see that coming out there. All right, there's also cyclonic storms that occur, like hurricanes and tornadoes, and also your hurricanes in the Atlantic. Katrina, obviously those of you in my Baton Rouge class have personal practical knowledge of some hurricanes, especially not just Katrina, but recently we've had a really bad one also. Really messed up the semester last semester we had to delay the start of the semester, and we had to do a lot of changes with the academic calendar, because some people were in the rain, and some people flooded out. Some people didn't have electricity for 3 weeks or so. Other people just didn't have internet for a few days. So there are all kinds of problems we had due to the hurricane. Typhoons in the in the Western Pacific, and then also tornadoes. Those of you in my Baton Rouge class, again, you have personal experiences I'm sure that you could share about tornadoes. If you're in my Eastern West Virginia class, you might have something as well. But tornadoes, not something that we typically have in California, but yeah, tornadoes are a result of systems fronts that are colliding. All right, so remember with climate variability, there is a natural climate variability, an expectation. And we know that because we have taken ice cores from glaciers, and those seem to be remarkably consistent records of weather patterns, of climate patterns over the years. Because what you can do is you could take the ice and analyze the ice and extrapolate and say, okay, well, if this much carbon dioxide, let's say, is in the ice and in the air bubbles that are in the ice, then you could extract that or extrapolate that and say, okay, well, then this is what happened at this point. And if you have an ice core, the deeper down you are, the longer the older the information is, because it's like if you have a stack of newspapers. I get the newspaper every day, and my wife reads it, but when she's done, she throws it in the newspaper pile, and so sometimes it gets a couple feet high before we toss it. And so if you were to look at that, though, the oldest newspaper is on the very bottom of that pile, and at the very top of that pile is just yesterday's paper. So ice cores are that way too. The information at the very top is the new information, and the information at the very bottom of the ice core is from a long, long time ago. Okay. All right, look at this, 420,000 years. You can see information from that far back. All right. And in taking a look at ice cores, there was information from the Little Ice Age of the 1400s. And what this tells us that, it doesn't have to be thousands of years where you have this climate, but it could be a short period of time. It could be a few decades long. It could even be shorter than that. But we sometimes think about, oh, well, the climate 2 million years ago was such and such, and it must have lasted for another million years. Well, the information we have from ice cores says no, it could change pretty quickly for a much shorter amount of time. All righty. This is an aberration called the Milankovitch cycle. But as we take a look at this, you can see in the picture that the Earth is not always at a 22 and a half angle, but the axis sometimes goes to 24, so it has a little bit of a wobble to this tilt. As you can see here, it says axial wobble, and in this diagram you can see that the Earth may be closer or further from the sun. It's not a perfect elliptical orbit that doesn't change. It does have some movement to it. So, so these would also explain some of the climate patterns that we have. All righty. And so the ocean also has a cycle. There are also decades-long oscillations in the oceans and the atmospheres. There's certain patterns of current movement that we expect, but these may change and even reverse in some cases. Uh, but this may change for a little bit at a time. And so the climate might change for years, even decades, because of the change in the ocean circulation patterns. All right. An example of this is the El Nino, or the ENSO, which stands for the El Nino Southern Oscillation. And so that's when we remember years ago, maybe 10 years ago, we used to blame everything on El Nino in California. Even the Lakers losing or something like that. Okay, the El Nino is when the warm surface waters in the Pacific Ocean move backwards, it seems, to South America. And what you'll see is that as the waters go across, the equatorial waters go back towards North and South America, then uh, the the currents get pushed up along the eastern part, the eastern part of the Pacific Ocean, and that would be the west coast of Central America and North America. And as the currents come up there, we're used to getting some cold water from Alaska, but then you start getting those warm waters during a El Nino event. You'll see fish that you never expected to see in even Southern California. So that's one of the effects of El Nino, when you have that reverse of the current and you have the warm water coming up instead of the typical, in the northern Pacific, you typically have a clockwise movement of water, which means that water coming down from Alaska, from the western coast of Canada, which is cooler, obviously, as it hits the United States, then that you typically have a cooler water. So where I grew up in Central California, when we would go to the beach, it was never really, really warm beach like the Miami beach I was telling you about. It was usually quite cool, but during a El Nino event, you have some warm water coming up from Mexico, and that's really a nice change. All right, so the third bullet says southern waters or surface waters driven westward by trade winds allow upwelling of cold, nutrient-rich waters off the west coast of South America, and that's what I'm talking about when it comes to the upwelling that helps the fishing industry off the coast of Chile and Ecuador. That area, you're going to see the upwelling, and then you're going to see have more fish than stronger fish catch those years. Okay. All right. And as I mentioned fish effects of El Nino in Southern California, but in the Western United States, during an El Nino year, it's typically a much rainier time. In Southern California, we have what's called a Mediterranean ecosystem, or even in this part of California, what we have is we have a short rainy season, but we don't expect rain during the summer like a lot of you do, depending on where you live in the United States. But when you have an El Nino, you do get a much rainier time. Between October and February, you might have a notable increase in rain. Alrighty, and then in between the El Ninos, you have La Nina, and that's the had the opposite effect, if you will, hot and dry weather. And so the effects of La Nina years between El Ninos might be, increase in hurricanes and such. as you can see, the surface temperatures of the ocean uh, might cause hurricanes to be even more violent than they are. And here's a diagram that shows it. This shows you the upwelling that happens right there as the cold water comes up. That's what we mean by an upwelling. And this is typically what happens. The trade winds go across from east to west. And so that is the typical pattern. But then what you see in this diagram here, in an El Nino event, what you're going to see is the circulation is going to stall out. And over here, you're going to have a much rainier time during an El Nino season, as I already said. Alrighty. These recent changes are unusually rapid, and this is because of the climate change. And it says here, many scientists believe that anthropogenic climate change is the most important environmental issue of our time. Anthropogenic means of human origin. So this has been known for a while. Since 1957, an increase in the carbon dioxide level from 315 parts per million to almost 400 parts per million 10 years ago. Okay, so we could double the atmospheric carbon dioxide levels within a century. That could have drastic, tragic events. You can see here, what's important to look at is the temperature, which is the solid black line that's going up there. No, what is that? That's the carbon dioxide levels increasing and increasing. And over here, the purple blue line that is going up. Along with that, you can see the trend for all of these measurements are just increasing. Look at this, the IPCC, the Intergovernmental Panel on Climate Change, says that there's a 90% probability that climate changes are due to humans. And we could probably 2 to 4 degrees Celsius, and if you're not a metric person, 3 to 8 degrees increase in temperature. That sounds actually quite alarming. If you can consider where you are and add 10 degrees to where you are, does that sound great? It does not. And if it's a 10 degrees increase, that's in Fahrenheit. Like if it's a 2 to 4 degrees Celsius increase, this is kind of telling. There's been a 5 degrees Celsius rise since the last ice age. So we're going to add another 4 on top of that. That's going to be, very warm. Here are the effects: more people with more extreme weather, floods, heat waves, hurricanes. It sounds like Louisiana. These could have disastrous economic and human cost. Look at this one though, sea level rise of 0.6 meters. That is, what is that? That's about 2 feet. So low-lying coastal cities like New Orleans, Miami could be affected. If you look at the elevation in New Orleans is, a lot of it's under the sea level, average like around, 6, which is what we said. If you take a look at this picture, this is a projection. The current shoreline, here's the coast of Louisiana right there. All right, there's Lake Pontchartrain right there. Look at this, New Orleans is barely out there. And this is when? By 2100. So it's, you might live to see this, I'm not, but you might live to see it. Here's Miami. And then here, look at this big chunk of Florida. It's now underwater. See Everglades right there. So that's a projected sea level rise by 2100. I remember though in the 80s, when I first started teaching, they said by the year 2000, there's a more than 60% chance of an earthquake happening in Southern California at magnitude 6 or higher. What did we have? We had in 1994, we had a pretty good earthquake. but nothing real big yet, so we're still waiting here. But the other thing was a 60 feet rise in the sea level possibly. So those of you in my uh, College of the Canyons classes, all right, we're 1,300 feet up. We used to joke back then that, you should buy some property in Palmdale, Lancaster. It's going to be oceanfront property within your lifetime. Woo! That'd be something else. I think that's why all the people moved out to Palmdale, Lancaster in the 90s. But that, thankfully, the ocean level did not raise that high. But some of those people are still in Lancaster, Palmdale because of the economic environment. Speaking of environment, yeah, but that's another lecture for another time. Carbon dioxide is the most important greenhouse gas, but it's not the only one. Okay, carbon dioxide is released from the combustion of fossil fuels. But we also know that methane is a big contributor to greenhouse gases. Well, is a greenhouse gas that contributes to climate change. And it's said that the numbers may be different from what I remember, but I remember reading something that said that there's 40% of the methane in the atmosphere is due to the flatulence of cows and livestock. Huh. Wow. And then others will tell you, well, then in order to decrease that, we should all eat lower on the food chain, and that is evidence, or that's an argument for a vegetarian type of lifestyle. So methane, and these are the greenhouse gases. Remember that water is one also. Computer models provide evidence of human-caused climate change. If you take a look at some of at the diagram for this one, that's what's telling for me. Let's take a look at that as we look if you take a look at the key at the bottom here, it says models using both natural and anthropogenic forcings. Okay, so that's in purple there, but then blue, or what is that? That's pink. But the blue is only natural. So if you have natural and then you have natural and humans, you can see that, well, then it's because of humans that we have this global warming, because this is without human influence, and this is with human influence, more so on the land than in the ocean, which makes sense. But globally, you still see a significant change. So climate models tell us, yeah, the atmosphere is changing. There is global warming, and it is due to people. So, all right, why should you care? Well, let's take a look at some ideas there. The idea of climate change is overwhelming, and if current trends continue, it most likely will be hotter than any point, and check this out, in the last 2 million years, and that's because of the way we live. Wow, that's pretty, I don't know, it's mind-blowing, isn't it? The average global temperature climbed 1 degree Fahrenheit in the last century. 19 of the 20 warmest years in the past 150 years is when we have reliable data, have occurred since 1980. Poles are warming the fastest. Permafrost is melting. People's houses are falling over. Climate change observations. The Arctic Sea is, the ice in the Arctic Sea is half as thick as it was 30 years ago. Polar bears, you seen that? that Coca-Cola commercial, and that polar bear's trying to swim. And he doesn't have anything to swim. They can swim like 50 miles, they say. But now to go from from a large piece of ice to the next large piece of ice is swim and swim and swim, which is the reason why polar bears are dying out. Ice shelves are disappearing, so the number of penguins has reduced. Look at this, 50% in the last 50 years. And penguins are one of my 3 favorite animals. Just so you don't have to wonder, my other 2 are sea otters and gray whales. Okay, glaciers are retreating all over the world. The oceans are absorbing and storing more heat. Oh man, I just read if you're in my canyons class, you're probably reading the Sixth Extinction novel, series of essays. Very disturbing reading in certain ways. If you'd like to read a New York Times best-selling book about extinction, which is occurring right now, the 6th extinction, then I highly suggest that. Sea level has risen 15 to 20 centimeters, not much, in the last century. And oceans are absorbing some of the extra carbon dioxide, but that is acidifying the ocean and damaging corals. Even a change of 0.4 in the pH is wow. It's just not just damaging, but destroying the coral reefs. And they say that by 2100, that there just might be just very few coral on Earth. Observations of climate change, different things happening, growing seasons are changing and all over the place. Some are lengthening in the northern hemisphere. Timing of different things. Some animals are breeding earlier. They're extending their range, whereas others are disappearing because they don't make it. In biology, we say that there's Gauss's law of competitive exclusion. You could win against competitors, or you can move to a different location, or you could just die out. Droughts are more frequent and widespread. Storms are more severe. I don't have to tell you Louisiana people about storms recently. Drought, if you're in my California class, third year, the California drought. Here in Southern California, we just changed from you can water your grass for 2 days a week, and it just went to 1 day a week. So, it's horrible. Animal breeding, migratory schedules, they're all changing. Everybody, all the organisms need to adapt to this change in climate. If you don't adapt, then you have the risk of going extinct. If you want to get taxed on it, well, this slide says better now than later. Look at this. The cost would be 0.5% of the gross domestic product. But if we wait, it'd be 20%. We need to cut. Energy production will need to be 80% decarbonized by 2050, just to stabilize the climate. So can we do it? Well, in developed countries, maybe. What about the poor countries? 200 million people will become refugees because of floods or drought. Extremes. 4 steps for combating climate change. Emissions trading. You read about that and see that on the news about carbon, meaning carbon demands and carbon levels. technology sharing with less developed countries, reducing deforestation, which we have done, but we need to do even more, and helping poorer countries respond to climate change. Why should they change what they're doing? They're just trying to live. Well, they can't. So we've got to make it so that they can make decisions that are good for climate change instead of, burning this coal in an inefficient way. Well, then maybe we could help them with technology so that they could sustain themselves with solar energy, something like that. Flooding, storms, and disease. Look at this. 100 meters, flooding coastal areas where a third of the world's population live. If you think of the United States, where's everyone live and where's everyone want to live? Well, they want to live by some ocean. If it's oceanfront or waterfront property, a third of the world's population lives there. Okay. Here's some info about the Kyoto Protocol. This is an illustration of where environmental science, unlike other sciences, has an aspect that has an opinion aspect to it and a political aspect to it, more so than other sciences. So this is a Kyoto Protocol where nations were called to roll back carbon dioxide, methane, nitrous oxide, and other greenhouse gas emissions by 5% below 1990 levels by 2012. And we didn't pass this. Okay, and it looks like neither did Australia. But, should we have? And that's the things that we look at. History will remember whether we made the correct decision or not. I was mentioned carbon trading earlier. And so carbon trading between even countries, you could take a look at emissions, carbon emission. New Zealand is touted as an area that wants to be a carbon neutral country. And hopefully they'll make that very soon. There's been reductions by many countries. The UK, for example, has reduced their carbon footprint tremendously in the past 15, 20 years. Stabilization wedges could work even now. We don't have to wait till later. We could do it now. Smaller pieces, smaller solutions to reducing the amount of carbon dioxide. Look at these. These are kind of interesting. To stabilize carbon emissions, we would need to cut 7 gigatons over the next 50 years. That sounds like a lot, but look at these ideas. If we could double the vehicle efficiency and halve the miles we would drive, that would save 1.5 giga out of the 7. We could save 1.5 this way. However, think about it. Are you going to really cut the number of miles you drive in your life right now? Vehicle efficiency, is that something that government needs to legislate? Or can we motivate car companies, automobile industry? Can we motivate them with governmental subsidies? And this again is where environmental science has an opinion aspect to it. Can we do this? Energy efficient appliances, better light bulbs. You probably have some weird looking light bulbs these days that is left over from when we switched over to CFT light bulbs. And now we have these LED light bulbs that they can make in all kinds of shapes, but they're much more efficient. Okay, is that hard to do? It's a little costly when you first do it. Light bulbs used to be $4 for $4, but now I can buy a really good light bulb for $15 that could last for, what's it say on the box, 12 years or something. Do I want to pay up front so much compared to what I used to? Well, you could save 2 gigatons of it. We all do it. Take 340 million people in the United States and we're all doing it. Yeah, we could save a lot. Capturing and storing carbon emissions from power plants and gas wells could save another gigaton. So if you look at just these 3 suggestions, that's 2, 3.5, 4.5. You're almost at 7. Here's some other ideas right there. We take a look at those and see if you can do anything about that. Depends on where you live. Look at this, add 2 million 1 megawatt windmills, 50 times more than what we have. Very windy areas in Southern California. There's some near Barstow. You have some by Palm Springs. My last trip to San Francisco, I drove past some by Tracy, California. So yeah, there's an opportunity to do that. I watched a documentary about, I think it was the Netherlands that even puts these windmills out into the ocean where it's really windy. And so they have wind farms that are not even on land. So you're not even using up your usable land, but you have them in the ocean. That's pretty neat. Alternative practices can be important. So this slide talks about carbon capture and storage and the unique ways to do it. I think you can see it better on the diagram. And you can see that here you have carbon dioxide that's pumped into disused coal field, displaces methane, and then the methane gets pushed up, so it's easier. Same with oil. If you pump the carbon dioxide into the oil fields here, it gets pushed up, and it's easier to take that out. How about this one? Don't do this for drinking water, but you can take carbon dioxide and pump it into saline aquifers. These are, when this is by the ocean, you might have a salty aquifer, and so you could pump that carbon dioxide in there. Those are pretty ingenious ways of getting rid of carbon dioxide and not just pumping it into the atmosphere. Maybe we should concentrate on methane also. This slide says methane instead. I probably wouldn't say instead, but carbon dioxide does get all the press, and we could also reduce methane emissions, and that would reduce global warming as well. And then the third bullet, as mentioned earlier, reducing the number of ruminants. Reducing the number of cows. Yeah, the reliance of the American diet on meat. That could help. Are we willing to do it? That's the question, isn't it? So here's what some other countries are doing. The UK has rolled back its carbon dioxide emissions to 1990 levels already. Look at that. That's pretty good. Oh, I mentioned this earlier. New Zealand wants to be the first carbon neutral country. Germany has reduced carbon dioxide by 10%. What are we doing in the United States? That's a thing. Denmark is 20% of its electricity from windmills. And now it's going to crank it up to 50%. China reduced its emissions 20% between 1997 and 2005 because they burn coal more effectively. I think it went from something like 35% to 60% effective or efficient, not effective. And then individual cities have pledged to reduce carbon emissions, reduce their carbon footprint. So that's great. And here's some things that you can do. And if you look at it from the top down, would you be willing to drive a fuel efficient vehicle? I would. If someone wanted to give me a Tesla for free, wouldn't that be cool? Okay, so not for free, but would there be government incentives, or would the economy be in such a situation where the price would come down dramatically and people could afford it without going into massive debt. What about carpooling? Can you do that? That's pretty easy. Or trip chaining, and instead of driving to the store every time you need one thing, write it on your list. And when you get to 20, then you can drive into town. I don't live right where the stores are. Every time we need something, if I go in every time, it's a lot of gas. Make your home more efficient, make your driving behavior, just starting and stopping. There are many things that we can do. And so here's a list. You take a look at it, see if you're willing to do anything, if anything is practical for you. And you can see the potential emissions reduction just by changing your behaviors. Whew. So climate change, is it for reals? Well, in this talk, we learned about different aspects of the atmosphere. So now you know something about climate and weather and how it's influenced by characteristics of the atmosphere and composition of the atmosphere. And we looked at climate change, and we saw that it seems like that is a thing and that it is actually occurring. And we saw some of the effects that may be seen in the next 40, 50 years due to climate change, maybe up to 2100, and then, it's not all gloom and doom. We can change some of this. We can stop it if we're willing to do it. And so these are all things to think about when it comes to environmental science. So I hope I gave you something to think about. And climate change, what can we do? What can you do? All right, well, have a great day. And it was good seeing you in class today. And we'll see you next time. I'm Mr. Vallejo. Bye now.